Let's look at another definition. This is a definition of the set of powers of an element. So we are looking at the set of powers of an element from a group. So we have G a group and we take an arbitrary element in that group. Then we define these brackets A as the set of A to the n, where n is any integer. If G is a multiplicative group, so if we have a multiplicative group, then we are using that power notation. And that's what we mean. If G is an additive group, then we use the same notation with this bracket A, but there our operation is addition, and so really we are repeatedly adding A to itself. So we get A plus A, A plus A plus A, A plus A plus A plus A, and so on. And so that we've seen before, we can also write as NA. We have really n copies of A added together. Let's look at an example again to illustrate how this works with some of the groups that we've seen before. So let's look at example 3. For each of the following groups, we're looking at two different groups in A and B, choose an element in A and calculate what this bracket A looks like, this set of powers. Okay, our first group we looked at the previous few examples. It's U7 again, under multiplication mod 7. And let's look at the set of powers of 2. Let me fix my bracket a little here. So what is that? Well, it's a set. It has stuff in it. And what it has in it is it has powers of 2. So, and what powers? Well, we have 2 to the 0. We have 2 to the 1. We have 2 squared. We have 2 cubed, and so on forever. But we also have negative powers. We have 2 to the minus 1, we have 2 to the minus 2, and so on in the other direction as well. And this is a good time to remember what that notation actually means in the context of this group. We are really talking about the inverse of 2, the inverse of 2 squared, and so on. So what are these numbers? We already computed a bunch of them. To 2 to the 0, that is our identity, element 1. 2 to the first power, that's just 2. 2 squared is 4, and 2 cubed, that was 1 again. We have computed that repeatedly. And 2 to the negative 1, that is the inverse of 2. And the inverse of 2, if you look at the Cayley table, that is 4. And you can also find the inverse of 2 squared and convince yourself that that is 2, and so on. Actually, I'm going to write one more down. 2 to the minus 3, that is the inverse of 2 cubed, but that is the identity again, 1. So we have a lot of repetition. We only have 3 different things in this set, and if we are looking at a set, we only need to write everything down once. So this is 1, 2, and 4. Hey, that is one of the subgroups that we encountered before. So this is one of our subgroups that we've seen before. Let's look at the set of powers of 3. And if you like, pause the video and do this yourself, but you can convince yourself. I'm just going to start with 0. The negative powers are not going to give us anything new when we are looking at finite groups. So let's just write these down. And this gives us 1. It gives us 3. 2. So this is from the work that we did in example 1. We already computed all these powers, so you can go back and just copy those down. That's what I'm doing right now. 6, 4, 5, and then you remember eventually we cycled back to 1. So this is what we have. Look at that. When I write this down, as a set, and if I put them into the right order, I have 1, I have 2, I have 3, I have 4, I have 5, and I have 6. That is all of U7. It looks like U7 is actually generated by this element 3 and all of its powers. So this is worth writing down. We have all of U7, and 3 generates the whole group. We actually call G a generator. G is a generator of U7. This is something that you want to remember. Let's do one more. Let's look at 6 and all of its powers. That's not much work. So we have 6 to the 0, we have 6 to the 1, we have 6 squared, and so on. And when you write those down, you get 1, 6, 1, well, 6, 1, 6. We don't need to write all of them down. This is really just 1 and 6. Okay, that is also one of our subgroups that we've encountered before. So I said this, but I'm going to write it down. Note that if the order of an element is finite, we need to only look at non-negative exponents. We definitely need to look at 0 to get our identity. But we don't need to look at the other one, the negative one, to generate all of A, of that set of powers generated by A, because the negative powers all denote inverses, and they are not going to give us anything new that we don't also already get through the positive and 0 exponents. Okay, so that much for the multiplicative group, U7. Let's look at the group of integers under addition, and there the notation is a little bit different. So we're only going to look at a couple of things here. What would it look like, the set generated by 2, the power set generated by 2? Well, what do we have? We have 0 times 2. So now we use this notation of NA. So 0 times 2, we have 1 times 2, we have 2 times 2, and so on in one direction, and then minus 1 times 2, minus 2 times 2 on the other direction. And what do we get? When I write all of this down, we have minus 4, we have minus 2, we have 0, we get 2, 4, and the next one would be 6, and so on. So this seems to be all the even integers. If I look at the same thing with 1, so at this power set, the set of powers of the element 1, in the integers under addition, I actually get all of the integers. So this would be a convenient way to write down all of the integers using this idea of powers of an element. So here we are. And in this case, 1 is not the identity. In this group, 0 is the identity because we are looking at an additive group. Okay, so this gives us all of C. And this is notation that we will be using